By now, we've absolutely squelched any remaining suspicion that you might have in your mind that the dark matter, evidence for which we found in the dynamics, the motions of galaxies and clusters, could possibly somehow be ordinary matter that was somehow hidden. It can't be gas or dust, because gas and dust would fall into clusters of galaxies, heat up, and we would be able to see it in X-rays. It also very probably cannot be ordinary stars, brown dwarfs, white dwarfs, neutron stars, or black holes, because those lead to microlensing events, which we search for and can't find. Finally, the real reason we know that ordinary matter in some hidden form can't be the dark matter that we have evidence for is both Big Bang nucleosynthesis and the cosmic microwave background put a very tight constraint on how much ordinary matter there is in the universe. It's only 5% of the critical density, but the dark matter is something more like 30%. We have to, in other words, turn to some unordinary kind of matter, some new kind of particle. So in this lecture, we're going to get serious and start saying, what kind of particle could be the dark matter? We have to go beyond the particles that we have already established exist in the standard model of particle physics. So what are the requirements for a new dark matter particle? Most obviously, it must be dark. The other important requirement is that it must be cold. So dark means not only is it hard to see, but it doesn't interact very much. When you look at a galaxy, the shiny part of a galaxy, the part that is easily visible from stars, comes from the ordinary matter, of course. The reason why the galaxy is able to contract is because ordinary matter interacts. Ordinary matter, in the process of collapsing under its own gravitational field, will get stuck. When one little bit of ordinary matter comes into contact with another one, it can cool off and settle down into the bottom. Dark matter seems to be distributed in a big puffy halo around the galaxy. It's not condensed right in the middle like the visible matter is. The explanation for this is very easy to come up with. It's that the dark matter particles just pass through each other and go right out. So dark matter needs not only to be dark, it needs to be not interacting with itself in any obvious way. The other requirement for the dark matter particle is it should be cold. In other words, even if the dark matter existed and had a small mass, but it were moving at a very fast velocity, if it were moving close to the speed of light in the early universe, then when it tried to collapse, it would go right outside and keep going. It would not oscillate back and forth like we want a real good dark matter particle to do. So we're trying to invent a new kind of particle that is dark and is cold. Let's just check that there's no such particle lying around in the standard model. Well, which particles in the standard model are dark? Of course, we don't want the ones that decay. Neutrons would not be good examples of dark matter particles because they decay away. You need something that will stick around. The only neutral particle in the standard model that is stable is the neutrino. Neutrinos are a very obvious place to look for a dark matter candidate. However, as it turns out, when you go to the details, because neutrinos are so light, they are not cold. When neutrinos decouple, when neutrinos freeze out from the primordial plasma at very early times, they're moving very, very fast. So they qualify as hot dark matter. If the dark matter we observe is hot, then structure on small scales in the universe doesn't form. You don't make galaxies in the universe which is mostly hot dark matter, because whereas the stuff would want to collapse, the neutrinos are moving out very, very quickly and tend to smooth everything out. Hot dark matter is actually quite strongly ruled out as a possible way for the dark matter to behave, so much so that these days we turned around. We use cosmology to place a constraint on the mass of the neutrino. If the neutrino mass is too big, it would be the dark matter, but we know it can't be the dark matter because the dark matter is not hot. So that's a good way to get an upper limit on how big the neutrino mass could be. So that's the only possibility in the standard model of particle physics. We need to turn to particles beyond the standard model. So let's think of what the requirements are on those particles. Of course, they must be dark, they must be cold. But in Lecture 9, we gave you an explanation for how to calculate the relic abundances of particles that are left over from the early universe. If a particle interacts strongly in the early universe, then the particle and its antiparticle will all annihilate away. And by the end of the universe's history, by today, we won't have anything left over. So what you need for a particle to be left over in sufficient amounts to be the dark matter is a particle that does not annihilate very strongly, a particle that is weakly interacting. Now, when we say weakly interacting, you might think, and it might be perfectly sensible, not interacting very much. It doesn't interact very often when two particles come together, and that's true. But now let's actually plug in the numbers. Let's do our calculation of what kinds of particles give rise to the right abundance of a particle today to be the dark matter, and ask how often should particles annihilate in order for them to be good dark matter candidates. The answer is that the right rate of interaction for a new particle to be the dark matter candidate is exactly that it would have if it interacted through the weak nuclear force. So when we say weakly interacting particles are good dark matter candidates, we don't simply mean particles that don't interact very much. We mean particles that interact via W and Z bosons, particles that interact via the weak interactions of the Standard Model. It's not the only possible way to get dark matter, but it's suggestive. It's telling us that if we invent a new particle that is stable, that is not interacting through electromagnetism or the strong interactions, but does interact through weak interactions, it is a natural dark matter candidate. So the name attached to such a candidate is a weakly interacting massive particle, or a WIMP, as opposed to the machos, which are the compact collections of ordinary matter. So we want to make WIMP candidates. We want to make new examples of particle physics that give us weakly interacting massive particles that are stable and could be the dark matter. For most of this lecture, what I'm going to do is talk about one specific example of a particle physics model that naturally leads to a candidate WIMP dark matter particle. This specific example is called supersymmetry. But really what you should be getting out of this lecture is not the details of supersymmetry as a candidate way to get dark matter. It's just an example of the kinds of thought processes that physicists go through when they're trying to invent new particles. The point is that you don't want to just say, well, yes, there must be some particle and it's the dark matter. Particles have interactions. Particles come with different properties. We know a lot already about the particle physics of the Standard Model, so when you're inventing a new particle, it has to fit in somehow. The best dark matter candidates will be those that have some natural interpretation in terms of particle physics all by themselves, even if we didn't know that there was such a thing as dark matter. Supersymmetry is an excellent example of that, and that's why it's worth going into it in some detail. So supersymmetry is a hypothetical idea which invents a new symmetry onto the symmetries we already know about in the Standard Model. We already mentioned that the Standard Model of particle physics is characterized by a great amount of symmetry. For example, the most obvious thing that you see in the Standard Model is that when you look at the fermions, they come in three generations. You have the up and down quark in a doublet, the electron and its neutrino in a doublet, and all by themselves, those four particles form a self-contained set. Then you have another four particles which repeat that pattern, two quarks and two leptons, the charmed and strange quark and the muon and the muon neutrino. And then it happens yet again, with the bottom quark and the top quark, the tau and the tau neutrino. So the fact that you have a similar structure repeating itself over again is an example of a symmetry. And at a deeper level, symmetries are responsible for the forces between particles, the strong nuclear force, the weak nuclear force, and the electromagnetic force. So supersymmetry is a very specific kind of symmetry, a different kind of symmetry than we have ever seen in the Standard Model. It's a symmetry that relates